Brilliant. Thank you everyone for coming. Today is the final SPAAM seminar of 10. Our first speaker will be Grega from Maths, who's going to talk about combinatorial representations of spin systems.
Thank you. That is actually a bit misleading. I will only show one combinatorial representation, but there are multiple of them. So the first slide is very similar to the one from last year. So we'll start with a model that's sort of meant to model how magnetism works. So we have a lattice, this is some material. In this case, it's 2D, but this could be d-dimensional. But enough, we know most about these things for dimensions 5 or greater. So we have a square lattice, and at each point in the lattice, to each point we assign a spin. So it's either spin up, which is a red arrow, or spin down, which is a blue arrow. And this then gives a configuration. This is this thing with so sigma is a vector that assigns either plus or minus 1 at each side. So that's the configuration. And then to each configuration we assign an energy. This red thing. H here stands for Hamiltonian, which is standard name for physics for this object. So you can see that we multiply the values of spin at two neighboring sides, x and y, and then give a minus, because intuitively what we want from physics point of view is if the spins are aligned, we want them to have low energy. So that's where the system wants to go to, always wants to go to lower energy. And so if all the spins point in the same direction, sigma x and sigma y will always be 1. So we're just summing ones, then add a minus sign. If sigma 1 and sigma y are two neighboring sides have opposite spins, then the product is -1. And then the first minus, you get something positive, which increases the energy, which is not what the system wants. And once we define this energy, we can fix some temperature T. More or less everything will depend on the temperature of the system. And then that sort of energy induces a probability distribution on our space configurations. So the probability of system being in some configuration sigma is proportional to this exponent of minus inverse temperature times the energy of the configuration. This, I won't get into why this is the case, but this is motivated by physics. So sort of physical property. Very briefly, these sort of things, this probability shows that if you look at some two blocks that are very far apart, the probability of each block being in some configuration will be that those probabilities will be independent. Far apart. This is what is this. And then what we're interested in is if you look at spins at two sides 0 and x, and if we make this side distant, so it means that we increase the size of the lattice to the entire ZP, which we call this infinite volume limit. And if we then set x to infinity, so basically we look at what is the product of spins at 0 and some very distant side. We want to see what's the expectation of it under this probability measure. So if the spins are likely to align, then this expectation will be some positive number. If the spins are likely to misalign, this will be some negative number. And if it's equal probability of them aligning or not aligning, which means they are independent, this here should be around 0. And this then, depending on how that expectation decays, this implies whether you have a long range order in your system or not, which then implies whether your material is magnetized or not. If it's magnetized, most spins point in the same directions, so that expectation will not decay. So this is what it actually looks like. So it turns out so this sketch is black dots represents speed -1, white represents speed 1. And it turns out that there exists some critical value for the temperature where your system changes behavior. So at low temperatures, it turns out that you usually have some ordered state. So for example, you might have some blob of spins pointing in some direction, and then all the other spins will point in a different direction. And if you then look at this expectation, this doesn't decay. You set x to infinity. It will be either -1 or 1, or at least some positive or some non-zero constant. So bar away from zero. If we then increase the temperature, which intuitively means the system has more energy, the system has more kinetic energy in it, then the energy contribution from spins being aligned or misaligned doesn't really matter that much anymore, which makes the system more likely to misalign, because that's just a small contribution to its energy. At that point, you get a disordered state, and this expectation decays exponentially to zero. Under criticality, you get polynomial decay. And so this is an expectation on the previous slide. Here it's written out explicitly. So to get this expectation, you take the value of sigma x times sigma 0, you weigh it by its probability, and you sum over all configurations. This here is just a normalizing constant. This here ensures that if you plug in 1, you actually get back expectation 1, just to make sure that this is a probability measure. And usually the most difficult part is to show that you actually get a polynomial decay of specific power at criticality. Okay. And so one way to show this is by using something called a random current expansion. So now we'll first give a brief derivation of this expansion, this excitation. So we call our Hamiltonian H is a sum over all neighboring of spins over all neighboring sides. So we can sort of rewrite it as a sum over all edges. So that E of lambda, they're all nearest neighbor edges. So you look at every edge in your lattice, an edge connects to neighboring sides, and then have a look at what's the spin at both sides of the edge. This means, right, that we can break down, we can factorize the exponent of H lambda into a product of over edges. And we just look at the exponent of this product. So now recall that earlier in our probability measure, we look at expectations, we sort of summed over all possible configurations, and we were summing this factor, right? So if you now plug this in, you get sum over all configurations and a product over all edges, and we are summing this factor over here. So this is just by plugging the Hamiltonian in. Next, what we do is we Taylor expand this exponential. And we get this, right? So we have to sum from 0 to infinity at every edge. And last step we do is, okay, actually it's not the last step. We can exchange these two sums. So we can first sum over, let's say, a vector of natural numbers. So for example, nxy represents the power at an edge xy that appears in this Taylor expansion. So we first sum over all the powers. This is what we call random current, because to every edge it assigns an integer. So you can represent this as writing multiple edges. So we have this sum, we still have multiple edges. We have this factor that comes from Taylor expansion. And then now, instead of summing over all configurations at the same time, we can just sum over configuration at specific sites, right? We need to sum over configuration have +1 or -1 at each separate site. Okay. Any questions on derivations? It's not that important to remember exactly how to derive it, but this is also to show that this is not a difficult derivation. So this is just the last line copied. Right, so on the left, we have the object we started with, and on the right, we have the object we now have after Taylor expansion. Now, one thing to notice is if you just look at this red part, right? We are summing over, we have sigma x to raise to some power, and we sum over sigma x1 and -1. So then what this means is if that, sorry, something I didn't point out quite well enough, right? So what happens here is when we go from this step to this step, if you collect all sigma x's, right? Since this sigma x is raised to nxy for all neighbors y. So every site x will appear. So when you sum over all neighboring sites, right? Every site will appear as many times as it has neighbors. which is why we then, this power here, this is summing the power nxy over all neighbors of x. This is how we get this side, this sum. And now if this sum is even, then this sum over here will just be 2. And if this sum in the exponent is odd, then this will sum up to 0, because we will get +1 plus -1. And so what this motivates is this definition. So for every current n, we define what we denote partial n. We call these sources of n. We say that the sources of our current are all sites where the sum of all edges coming into the site, the number of all these edges is odd. Okay? And another thing we'll define is we will sort of pack this product into something we will call a weight of a current. So this weight only depends on the current. And now we can rewrite this top expression with this equation over here, right? So instead of summing over all currents, we only sum over currents that have no sources. As soon as a current has a source, we'll get a factor 0 over here, and we have a product over here. So the entire term here will be 0. So we only sum over currents that have that are sourceless, that do not have any sources. Because currents with sources have 0 contribution. And we're only summing this weight of a current, right? This is what I have to sum. And this product with this sum over here just ends up being 2 to the power of the number of sides, because we get a 2 at every side. So now we managed to rewrite this sum in a, let's say, something. It is, I mean, I will treat it as being simpler. Now, if we modify this sum by plugging in sigma x and sigma 0, the only thing that changes is that we're looking at this sum over here. We get additional +1 at x and 0, which means that this sum has to be odd at x and 0 to make the whole thing even. So if we add sigma 0 and sigma x, we then get that this is equal to the sum over all currents, when now the current has to have a source at 0 and a source at x, and it has to be sourceless elsewhere. And now this expectation, the thing we started with here, this expectation can, if we fix lambda, can now be written as a ratio of these two sums. So we sum over currents. In the numerator, we sum over currents that have sources at 0 and x. In the denominator, we sum over sourceless currents. Okay. Any questions? Okay, so now these are examples of 4 currents. So the currents in the top row are both sourceless. So for example, the fact that we have 2 edges over here would mean that if this is x and this is y, then nxy here would be 2. So this is one current, this is another current. This is a current that has a source at 0 and x. So for example, at 0, we have 3 edges in total. At x, we have 1, which is odd. And this one has 4 sources. Now, why is this useful? Well, there's some combinatorial trick we can do that ends up being very useful. This trick sort of gives some connection between sourceless currents of specific type and currents with sources, which is going to be useful when you sort of manipulate this ratio and this ratio and these sums. It's useful to know some connection between these currents. So the way this works briefly is, say we have some lattice, we have a current, and suppose we fix some plane we call Hn that goes to the middle of it. And we start with some current. And what we do is we will reflect the current on the right to the one on the left. So if you take this part on the right and reflect it, we get this part. This is x, and this is the reflection of x prime is reflection of x. Now, in this case, you can see that x is, after we reflect things, x is connected to this plane Hn. We can find the path from x to Hn. We fix a path. This is this red path. What we have to do next is, remember earlier when we were summing over currents, we had to sum their weights as well. It turns out that you can you don't have to sum over weights as long as you can represent each current multiple times. So what I mean by this is, in this case, let's say we have to color every edge with either blue or light blue. The light blue are the current that started on the right side and got reflected. The dark blue color is the current that was on the left side originally. So on the left photo, if we colored everything on the right in light blue and reflected it, we get this. But now we have to distinguish between, say in this case, between painting the top edge in light blue and the bottom in dark blue, or the other way around. So you need to distinguish, you can differentiate between your edges. If you do this combinatorial trick, then instead of summing over weights and over currents and then weights, you just sum over all these possible subgraphs, say, or all these possible multigraphs when you color things in every possible way, according to some restrictions. What you do next is, this is the path we fixed earlier on the left side. We switch the color on every edge in the path. So this becomes light blue, this light blue becomes dark blue, this dark blue becomes light blue, and this light blue becomes dark blue. And then you reflect back and you get some other current. It's not that important how this precision, it's not important exactly how it works, but the point is you start with a sources current that is connected to this HN, and you end up with a current that has a source at X and its reflection. And this is in some appropriate sense, this is a bijection. If you look at the appropriate class of currents, or it's a multigraph, this will be a bijection, which means that you're not sort of spoiling anything when you do this manipulation. You start with an object and you end up with the same object, you just represent it differently. Now, why is this useful? So how we use this switching lemma to get sort of the asymptotics I mentioned at the beginning, where it turns out that the probability of 0 being connected to HN, we can bound this from below. The way we can bound this is that the probability of this is 1 minus probability of 0 being connected to HN. If 0 is connected to HN, we can do this procedure and then show that this is equal to having a source at 0 and its reflection. But then going back, this means that if we have a source at 0 and its reflection, then that whole sum equals to this probability over here of 0 and 0 reflection. So X being reflected 0. And this is then equal to the expectation of spin at 0 and the reflection of 0. And I said earlier that this decays in the appropriate regime, this decays exponentially. It's a long-winded argument, but because you know that you're in certain regime at certain temperatures, because you know that this expectation decays exponentially, you can use this to sort of get some bounds of the currents that connect 0 and 0 prime. You can then use that to sort of say what's the probability of 0 being connected to HN, and you can use that to say what's the bounded probability of 0 not being connected to HN. And from this, right, we can then get this is what is set in here. So the expectation of 0 and of sigma 0 times sigma X, condition of X being connected to HN is this expectation. And now, if you look at this expression over here, this is just the expectation of so using that this over here, this expectation is equal to this expectation with the indicator that X is connected to HN. So this difference here is the same as saying that X is not connected to HN. We're just from 1 in here, we're subtracting the indicator that X is connected to HN. Okay, and because we have this bound, this probability of 0 not being connected to HN, this gives a bound on this expectation. Turns out we can also then sum over all sides in the box. And now, the reason this is useful is because if we know that if we have this bound for all C, so imagine this. So we know that if we have our expectation we want to analyze, we know that if we sum this expectation over all sides in a box, this is still bounded away from 0. And then we know that this holds for any n. So you can send n to infinity, and we get an infinite sum. Now, if your sum decays exponentially, now if these expectations decays exponentially, this will not be possible because okay, it's not really, yeah, I mean, this is not completely true. I'm skipping a few steps. Basically, the fact that you can get a sum for any n, and it's always bounded from below, gives a lower bound of how fast your things can decay. If they decay too fast, then they will not be bounded from below. If they decay, yeah. So basically, you can use this current to then get. You can use this current to sort of get a lower bound on this expectation here. Upper bounds are done differently. Okay, so that's it. Yeah.
Okay, thanks, Grega. Do you have any questions? No, could you I don't think I fully understood the last step of your reflection. Could you just explain that again?
Oh, this
Yeah.
so you start with this graph. Now you switch the colors along this fixed path. The reason this path has to be fixed is because you actually do this for multiple graphs, not just for this one, but for multiple ones. And then after you switch these colors, get this graph. So these two graphs are the same. The only difference is that the edges that are circled change the color. And now when you reflect, you only reflect light blue edges. And the dark blue ones stay here. So then you get this. Yeah.
So I think at this point you said it defined the bijection between graphs that could be connected to HN if you fold them over, and graphs that actually went all the way through and had the two sources. How do you define the choice of red paths on there?
You can be very
lots of choice.
Yeah, you can be very. What you do is just say, we can imagine we have some ordering on all the possible paths, and we choose the first one.
Fine.
So it doesn't matter. It doesn't matter how you set your path. It only matters that you know that it's consistent. So meaning if I gave you the same graph twice with different colorings, you would choose the same path every time.
Yeah. And when you say connected to 0, obviously at the beginning it's not connected to 0. So.
Oh yeah, so it's only connected after you reflect. Yeah, it doesn't have to be connected before.
Okay, so when it says connected to 0 in the next slide, that's like.
Oh yeah,
that means if
yes, if you fold it, yeah.
And 0 is neither x nor x prime here.
Well, they could be in principle.
Okay,
so
it's not on the reflecting line, it's something else.
Yeah. So for example, usually 0 would be further to the left, for example.
Okay.
So the reason this is called HN is, this is confusing notation now. Yeah, is because this plane would be a hyperplane with x value. Okay, again x, and away from 0 basically.
Okay.